Hello students, welcome to lecture 47 of the online course on Introduction to Microwave and Optical Metamaterials. In today's lecture, we will see about the principles of transformational electromagnetics. This is also popularly known as transformation optics because initially this concept was developed for that optics domain, but it can also be extended for microwave frequencies. So, we will discuss the introduction, fundamentals and principle of this field, taking transformational electromagnetics as the key term TEM, we can call it in the shorthand. Okay, then we will see how you do the coordinate transformation, that is from cylindrical to Cartesian, spherical to Cartesian and Cartesian to Cartesian, and finally we will look into that Maxwell's equation shows form invariance, and that is very important for this transformational electromagnetics or transformational optics to work. So, now let us look into what is transformational electromagnetics. So, this is basically a design technique that uses coordinate transformation to manipulate electromagnetic fields and allow you to design novel electromagnetic devices. So, by applying mathematical transformation to the space, this technique basically allows creation of devices with unconventional properties, something like invisibility cloaks, perfect lenses and beam steering devices. So, how do you realize this kind of devices? You can realize this kind of transformations by using metamaterials, which is the theme of this course, where you can engineer the properties of the materials because you do not need to rely on the natural materials and their fixed properties. So, the applications of transformational electromagnetics can be for invisibility cloaks, that is you can develop devices that can bend electromagnetic waves around a particular object, making that object appear invisible. Other applications could be like perfect lens that can focus electromagnetic waves beyond the diffraction limit. So, it can help you achieve much higher resolution and resolve very fine details of a particular image or a feature. Then you can also make beam steering devices that allows you to control the direction of the electromagnetic beam, such as antennas that can focus and steer the radiation based on your application. There are other applications as well that can be like reflectionless beam shifters. You can design beam splitters and also flat parabolic mirrors. Okay. So, if someone asks you what is transformational electromagnetics or transformation optics, the clear definition is it's basically a mathematical tool that facilitates the design of optical materials that can guide light along any desired trajectory. So, the underlying concept basically here relies on the geometrical transformation that can convert simple trajectories into your desired trajectory. So, in order that Maxwell's equation remain valid, the optical parameters associated with the transformed equivalent system must be modified, and this establishes the character of the required optical material. So, you can take one simple example of such equivalence. So, you can think of a local compression of the coordinate system by a scaling factor is going to be equivalent to the local increase in the refractive index of some medium by the same factor. So, that the optical path length, which is basically the product of the length and the refractive index, remains unchanged, right. So, that way you can think of how the local compression or expansion of a coordinate system can be mapped into the material property, right, and those materials you need to design using metamaterial. So, in summary, you can say that it's basically a 4-step design procedure. Okay. First, begin with a pilot physical system for which the optical trajectories are known. such as you can consider homogeneous and isotropic material. Then you find a coordinate transformation that converts these trajectories into your desired ones. Okay? For doing that, you have to determine the transformed physical parameters of the equivalent material, which can do the same kind of distortion to the electromagnetic wave or light. Okay? So, that should go into the material property, and then finally you need to implement that new material that will give you the desired electromagnetic trajectories in the original coordinate system. Now, since geometrical transformations generally involve changes of direction and introduce direction dependent scaling, the performed parameters are generally both isotropic and spatially varying. Okay? So, the principles of TEM tells you that the mapping that you will see between the old and the new system, that has to go into the material properties. Now, normally how you consider the light matter interaction or electromagnetic wave matter interaction, you consider the two basic parameters of the material, its electric permittivity or magnetic permeability. So, let us consider epsilon ij, these are now in tensor form, and mu ij be the elements of the, so ij will tell you one particular element of the tensor. Okay. So, this represents the permittivity and permeability tensor elements of the original material in the original coordinate system. So, you can say it is x1, x2, x3, or you could have named them x, y, z, okay, whichever you like it. Now, the elements of the permittivity and permeability tensors of the equivalent material denoted by the superscript prime, okay, in the transformed coordinate system. So, you can consider the unit vectors to be, or the coordinate system to have the 3 axes u1, u2 and u3. Okay, the unit vectors will be obviously u1 cap, u2 cap and u3 cap. In this particular coordinate system, you can correlate the parameters, the new permittivity and the permeability parameters to the old system using this formula. So, you can see the new permittivity epsilon prime will be A transpose epsilon A divided by determinant of A. Similarly, mu will be A transpose mu A divided by determinant of A. So, now what is this A and A transpose? A transpose is obviously it is basically the transpose of A. Okay. Now, A is the most critical thing here, we are coming to that. Before that, we have to just understand that epsilon and mu are basically a 3 by 3 matrix. That is why you can have this epsilon ij as each element, mu ij, I and j both are running from 1 to 3. Okay. Now, here is how A looks like. Okay. So, A is basically a 3 by 3 Jacobian transformation matrix. So, the elements are basically the partial derivatives. Okay, the partial derivatives of the new coordinate system divided by the old one. Okay. So, Aij equals dou ui by dou xj. Okay. So, I and j both are 1, 2 and 3. Okay. So, you can see that since A is generally dependent on x1, x2 and x3, so the equivalent material is generally inhomogeneous, even if the original material is homogeneous. So, in a special case, if you consider the original material to be both homogeneous and isotropic, say free space, in that case the epsilon and mu are basically diagonal and they have equal diagonal elements of epsilon naught and mu naught, right. So, in that case you can simply write epsilon naught inverse epsilon prime, that will be equal to mu naught inverse mu naught prime will be nothing but determinant of A inverse A transpose A. Okay. It is coming from the previous set of equations, nothing new here. Okay. So, what I just want to tell here is that the tensors epsilon prime and mu prime are then identical except for a scaling factor, right. So, each have their own scaling factor, right. So, this will remain similar. Now, under this condition, you can see the impedance, which is basically the ratio of this permittivity and permeability, that remains unchanged for all polarizations which in turn basically implies that the equivalent medium will introduce no reflection at the boundary with free space. So, this is the beauty of this transformation electromagnetics. You can define and make the material to work according to your desired plan for the wave trajectory. Now, let us move into coordinate transformation and see how it is done. So, we can basically map one coordinate space into another. Okay, so you can simply take this kind of a coordinate space where a position vector r is given as x x cap plus y y cap plus z z cap. Okay, that can be transformed into this kind of a coordinate space, okay, where r prime, the position vector, is now x prime cap plus y prime cap plus z prime cap, right. Now, we have seen that in doing this kind of coordinate transformation, what is the most critical element is the Jacobian transformation matrix A. Few places they also call it J. Okay. So, A is basically delta r prime transpose. So, this is how you can basically calculate each elements dou x prime dou x, dou x prime dou y, dou x prime dou z, that is the first row. Then you have dou y prime dou x, dou y prime dou y, dou y prime dou z, second row, and the third row is dou z prime dou x, dou z prime dou y, dou z prime dou z, right. Fine. So, what you see that Jacobian matrix does not perform a coordinate transformation on its own. It basically transforms the functions and operations between different coordinate system. For example, let us take a cylindrical coordinate system to a Cartesian coordinate system. So, this is how the Cartesian and cylindrical coordinates are related. You have all known this for a long time. So, x can be written as rho cos phi, y equals rho sin phi, and z remains z. So, I am not showing the regular picture of how a cylindrical coordinate system and a Cartesian coordinate system looks like. I believe all of you know that, right. So, my idea here is to tell you how the Jacobian matrix will look like. So, we are going from cylindrical to Cartesian. So, you see the denominator is basically having the old coordinate system, and the numerator is basically having the new coordinate system. So, this is how you can calculate the Jacobian matrix A. So, the first element will be dou x by dou rho, then you have dou x by dou phi, dou x by dou z, and so on. So, once you compute this, so x is basically rho cos phi. Okay. So, you can calculate dou x by dou rho as this, dou x by dou phi is minus rho sin phi, dou x by dou z is basically 0. Similarly, you can calculate dou y by dou rho is sin phi, dou y by dou phi will be rho cos phi, and dou y by dou z is 0. Okay. And then you can compute, because z equals z, there is no transformation. Okay. Along the z axis there is, okay, it remains same. So, you can simply have these two terms 0 and dou z by dou z equals 1. So, with that you can get, this is the Jacobian matrix that can be used to transform the functions and the variables from cylindrical to Cartesian coordinate system. Next, we can look into the spherical to Cartesian. Okay. So, the Cartesian and spherical are basically related like this. X can be written as r sin theta cos phi, okay, y equals r sin theta sin phi, and z equals r cos theta. Just for a quick recap, theta is nothing but the polar angle and phi is basically your azimuthal angle on the xy plane, right. So, once you know that, you can calculate the Jacobian matrix as A. This is a 3 by 3 matrix. So, you can calculate this as dou x by dou r, dou x by dou theta, and dou x by dou phi, because your previous coordinate system is r theta phi, and the new coordinate system, that is x prime, y prime, and z prime, are basically your x, y, and z. Okay. So, now you can calculate all these 9 elements. So, I will just take 1 or 2 examples. So, this is the first one, x equals r sin theta cos phi, this is the first relation. So, if you want to take partial derivative with respect to r, you simply have dou x by dou r equals sin theta cos phi. Okay. Similarly, if you take another one, say x and phi, so this is the relation. So you take dou x by dou phi, that will be minus r sin theta sin phi, right. Accordingly, you calculate all these 9 elements and you get this is the Jacobian matrix for this particular case. So this Jacobian matrix will help you transform the functions and the operations from spherical to Cartesian coordinate system. You can also transform between the two Cartesian coordinate systems. So you can say the new one x prime will be a function of x y z, okay. So this is how the Jacobian matrix will look like. So x prime, y prime and z prime are basically the new axis and x, y, z are the old axis. So this is how the transformation looks like. Now I have been repeating that Jacobian matrix can help you transform the vector functions and the operations. So let's see how it is done. So you take a vector function that is basically a variable that changes as a function of position, okay, in two coordinate systems, that can be related to through the Jacobian matrix using this kind of relation. So E prime r prime will be A transpose inverse of it times ER, okay. So you can simply write ER, this can be any field also, right, electric fields for that matter, okay. You can write ER is nothing but A transpose E prime r prime, okay. So that way any vector function can be transferred from one coordinate system to another coordinate system if you know the Jacobian matrix A. Similarly, if you take any operation such as derivative, integral, that can be also transformed between the two coordinate systems using the Jacobian matrix. So you can write f prime r prime, that is a operation that you are doing, okay. So f prime r prime can be written as A, and then you have f r, that is the operation in the previous coordinate system, then you have A transpose divided by determinant of A. So that way you can write that this f r, the old one, can be nothing but determinant of A times A inverse f prime r prime, that is the already transformed the function or the operation in the transformed coordinate system, into A transpose inverse. So what I am showing here is that using the Jacobian matrix you can transfer or convert the vector function or any operation between the two coordinate systems, and that is possible because of the form invariance of Maxwell's equation. So if you write Maxwell's equation in any coordinate system, that basically looks like this, okay. So in Cartesian coordinate system you have seen that curl of H is nothing but j omega epsilon E, and curl of E is minus j omega mu H, okay. Now if you change it to cylindrical coordinate system, it looks exactly the same, okay. If you go to spherical system, it exactly looks same. So we can transform Maxwell's equation to different coordinate system, but they will basically look exactly same. So you can write del prime, okay, curl of H prime, that will be equal to j omega epsilon prime E prime, again del prime cross E prime. So that is basically curl of H and curl of E in the new coordinate system, right. So this is the vector fields are also transferred to the new coordinate system, and the operation that you are taking curl, that is also transferred to the new coordinate system. Both actually follow the same form, because you can write curl of H in the new coordinate system as j omega epsilon prime E prime, and curl of E in the new coordinate system can be written as minus j omega mu prime H prime, okay. So we basically can absorb the transformation of coordinate transformation completely into the material properties, right. So that is the vital consequences of this Jacobian matrix and using this kind of coordinate transformation. So you can write the same sort of Maxwell's equation in the new coordinate system, okay. But what you can do, you can basically push all this coordinate transformation into the material property like this, and you go back to your old coordinate system. Now, you can go back to the old coordinate system, but in this case the fields will basically behave as if they are in the transformed coordinate system, because this and this are now equivalent. Okay. So, what are these new ones? So, I am basically talking about the new material property. So, these are basically this. Okay. So, I am just writing mu prime, that is the new material property tensor will look like A mu A transpose divided by determinant of A, and then you have epsilon prime that will be equal to A epsilon A transpose divided by determinant of A. So, we are basically now transforming an operation here, not a function, right. So, what is A? You can always you know that from which coordinate system you are going to the new one. So, you know what is your x prime, y prime and z prime, you know your old one x, y and z. From that you calculate the Jacobian transformation matrix, that is basically telling you that you are moving from a vector space of or you can say a dimension space of R to R prime, right. Now, let us prove this form invariance, because we just considered that it is correct. Now, let us see how it is done. So, if you take curl of E, you can write minus j omega mu h. Okay. Now, when you write this in the new coordinate system, you can simply write delta prime E prime equals minus j omega mu prime h prime. Okay. So, let us now define the coordinate transformation that you have r prime. This r prime is nothing but a function of r, right. So, you can write E prime r prime as A transpose inverse E r. This we have already seen. For magnetic field also you can write in the same way, and for the material property mu prime r prime, you can write it as A mu r A transpose divided by determinant of A. Okay. Now, we substitute our transforms into this curl equation. So, now instead of E, okay, you can write now A transpose E prime r prime. Okay. This mu can be written from here, which is nothing but determinant of A, okay, and then you have A inverse mu prime r prime into A transpose inverse, and H also you can write from here, it is nothing but A transpose into H prime r prime. So, this is basically now becoming as if you are doing the curl of A transpose E prime, and it is giving you minus j omega determinant of A inverse mu prime A transpose inverse times you have this term which is A transpose H prime. So, you can see that this is basically taking the form of this. So, you can divide it by determinant of A, and then you can take this guy on the other side. So, you will see that you are basically getting this kind of form, that you have A multiplied by the curl operator A transpose divided by determinant of A times E prime, which is equivalent to minus j omega mu prime H prime, right. So, if you recall the form of transforming an operation, it looks like this. You have f prime r prime will be equal to A f r A transpose divided by determinant of A. So, here also you are getting the same thing. So, you are basically doing, instead of this function, you are basically having the curl operation, right. So, this is nothing but your curl prime, okay. From the previous one, this is your curl prime, right, and then you have E prime, okay, and on the right side you have minus j omega mu prime H prime. So, you can simply write this equation as curl prime or del prime cross E prime, that is nothing but curl of E in the new coordinate system minus j omega mu prime H prime, right. So, if you have started with the Maxwell's curl equation, you would have written this, that curl of E r equals minus j omega mu r H r. Now, because you are using this transformation, that you are moving to r prime coordinate system. Okay, and the relation between the r prime and r system is that the r prime is the scaled version of the previous system. So, r prime is nothing but ar, and now you can actually do this shifting, that you can write er in terms of the new electric field, mu can be the mu prime in the r prime coordinate system, h can be r h prime. So, all these things can be done, and you also need to write what is curl operation in the new coordinate system. So, curl prime operation will be having this kind of transformation. So, you can calculate that, and you will see you are getting a 1 by a factor coming out from this matrix. So, if you put it back into the equation which has got all the transformed fields and operation, you will see that this kind of scaling that you have done. Okay. So, curl prime will come with a 1 by a, and that a you can actually push into the material parameter, and you can simply go back to your old coordinate system and can write curl of er, that is in the original coordinate system, will be equal to minus j omega a mu r, okay, hr. That means whatever is the transformation you are doing, that can be just pushed into the material property. So, the new magnetic permeability will have the scaling factor of a, okay, and you can go back to the old coordinate system. So, that will basically behave as if the original system has got this kind of a transformation. So, with that we will conclude here. If you have got any query regarding this lecture, you can drop an email to this email address mentioning the course title and the lecture number on the subject line. Thank you.